Hello guys, uh, this video will be about the Gauss's divergence theorem, and we are going to look at what it really is and uh, 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 what it really means uh, for its expression in three dimensions. So Gauss's divergence theorem relates the double integral flux over the surface of a vector field to the volume integral of divergence of the field. So this is what it really is, and this side over here, this is the flux. This part, that's the volume integral of divergence. So this equation is crucial in understanding the problems of electrostatics and of fluid motion. And so what we're going to do in this video is we're going to look at a very simple proof of why this is true, why this theorem is true. And firstly, we will start with an intuitive idea of what the uh, divergence of a field uh, means. So, if we have a field in three-dimensional space, and for this video, we will be speaking with reference of Cartesian coordinates. So, generally, so let's have a let's have a general contour in three dimensions. So at each individual point, the quantity divergence gives how much of the field is coming in or going out through that point. This is the intuition behind divergence. And when you do that through the whole of the said surface, what essentially happens is the corresponding neighbors cancel out, and we are left with the total flux through the surface. And now let us start with an actual proof of this, and a very simple proof, relatively simple proof. We will be discussing by starting with a vector E with x, y, and z coordinates and z components in 3D space. So if we look at a differential volume with, let's say this is dx, the differential, this part, the dy and the dz, and this is the set differential element and a field passes through it. Talking about flux, the net flux in X is times the area, which is nothing but dy times dz. So this is the net flux through our differential element in the direction of x. So what we are going to do now is the crucial part. We multiply and divide by dx. This will lead to the expression becoming 2 So this part over here will be our dp, the dx, and looking carefully at this part, well, this is nothing but the partial differentiation of the function, the component, the x component of the field. dE by dx. So this is the net flux in x direction of the small element. Similarly, the y direction and the z direction. Adding them all three will give the net flux, which is the expression this is the small flux, the small flux phi through the differential element, and when integrating over the whole volume we will get the result as the total flux being looking carefully at this equation, we see how it is just the dot product of the nabla operator and the field function, and hence we have derived the famous Gauss divergence theorem. And so this is about it, and thank you very much.